Welcome back to AI Paper Podcasts. Today we're diving into a really interesting one. It's called PretrainZero, Reinforcement Active Pretraining.
Yeah, by Xingren Jing and his colleagues. And it really goes after one of the biggest problems in scaling up LLMs right now, the data wall.
The data wall in reinforcement learning, right? So the core issue they're tackling is that our best post-training methods, things like RLHF and RLVR, they just hit this ceiling.
Exactly. They get bottlenecked because they need these super expensive verifiable rewards. You either need a human in the loop or a very specialized domain, and that just limits how much you can train.
And the solution they propose, PretrainZero, is, well, it's a completely different way of thinking. It's a standalone reinforcement learning pre-training framework.
Yeah.
So RLPT.
And it uses RL directly on just general, messy, real-world data. Think Wikipedia, no supervised fine-tuning, no external reward models. The whole thing is designed to mimic how humans do active learning.
The results are pretty staggering. PretrainZero just consistently blows passive pre-training strategies out of the water.
It really does. I mean, they took the Qwen 4B base model and boosted its performance by over 4 points compared to a random RLPT baseline.
And the raw gains are huge. A 10-point increase on math benchmarks just during pre-training. And maybe the most important part, it makes robust chain of thought reasoning just sort of emerge on its own.
So that's our mission today. We're going to unpack how they pulled off verifiable RL on noisy data and why this whole active learning idea could fundamentally change how we train models.
All right, so let's set the stage. The RL data wall. We all know the standard training pipeline, right? You start with this massive self-supervised pre-training.
Just next token prediction on, trillions of tokens.
Right. And then comes the specialized post-training phase. And that's usually where RL comes into play.
And that phase is powerful, but it's where the bottleneck is. I mean, if you're using RLVR, that's reinforcement learning with verifiable rewards, you need these complex domain-specific checkers.
Like for a math problem or a piece of code.
Exactly. And if you use RLHF, you're depending on human annotators, which is slow, it's expensive. And, if you run RLHF for too long, you get these other problems.
Oh, yeah, reward hacking.
Yeah.
Where the model just learns to trick the reward model instead of actually doing what you want.
You got it. So you're stuck. You want the benefits of RL, like better reasoning and safety alignment, but you're constrained by this verification data. It's a classic scaling problem.
So the natural next step, the goal here, has to be pushing RL earlier into the pipeline.
That's the idea behind RLAPT, reinforcement learning pre-training. The question is, can you take that powerful RL engine and apply it to the cheap, massive pre-training data sets we already have? Can you boost general capabilities right from the start?
And in doing so, you'd completely bypass that verification data wall.
In theory, yes, but it introduces a whole new problem, a huge one, actually.
How do you even define a reward? When you're just looking at a huge corpus of raw text like Wikipedia, what's a verifiable reward for good reasoning?
That was the first big hurdle the researchers had to clear. They called it vanilla RLPT. How do you construct that training signal directly from the text itself?
So they set up some baselines to test this. They took the Qwen 4B model, fed it Wikipedia, and tried 3 different sort of passive masking strategies.
Right. The idea was to see if a fixed passive strategy could even work. They tried simple next token prediction, randomly masking bigger chunks of text, and then one that seems smarter on the surface.
Entropy-based reasoning.
Basically, find the tokens that are the hardest to predict and make the model learn those. The hypothesis being, just fix a pattern and let RL do the work.
And it didn't really pan out that way.
Not at all. It really showed how inefficient passive methods are when you're dealing with noisy real-world data. First, they compared the 2 random approaches.
And the simple next token prediction actually beat the random masked span approach.
Which tells you that just masking a bigger chunk of text doesn't help if your selection is blind. You're probably just introducing more noise than signal.
But the real shocker came from the entropy-based method. The logic seems so sound, right? High entropy tokens are the most surprising, so they should be the most informative.
And on clean synthetic data, like the OmniMath dataset, it works perfectly. It forces the model to learn deep patterns.
But on Wikipedia?
Total collapse. The training just tanks. Reward degradation happens almost immediately. They have a great figure in the paper showing this. It's a critical finding.
So why does it fail so badly?
Because on raw, noisy data, high entropy doesn't mean challenging but learnable. It usually just means unpredictable noise. Punctuation errors, weird formatting, just garbage.
And if you try to force an LLM to learn garbage, the whole process just falls apart.
Exactly. So the conclusion was pretty clear. Passive fixed prediction patterns are just too inefficient. The information density is too low and the noise is too high. The model needs a curriculum that adapts.
It can't be a fixed difficulty. It needs to be an active curriculum.
That's the key insight. That's the genesis of PretrainZero. They decided to mimic human active learning. A student doesn't just read a textbook from cover to cover.
No, you focus on the stuff you don't know, the concepts that are right at the edge of your understanding. That's how you learn fastest.
And that's what they built. They framed the entire process as a coupled adversarial game, mask generation versus mask prediction. This is the core engine of the whole thing.
Okay, so you've got this min-max bi-level RL objective. It sounds complex. You're saying the LLM is basically playing against itself.
That's a great way to put it. The LLM, which is parameterized by omega, is running two conflicting policies at the same time. You can think of it as a student and a very demanding teacher.
Okay, so who's the student?
The student is the mask prediction policy. Its goal is simple: maximize its score. It tries to fill in the masked text, often using chain of thought, and its reward is a simple binary. Did it get it right or not?
An exact match. It's verifiable because the answer is right there in the original text.
Right. And then you have the teacher. Or maybe a better term is the devil's advocate. That's the mask generation policy.
And its job is to make the student's life difficult.
As difficult as possible. Its objective is to minimize the predictor's performance. It actively searches the text to find a mask that is perfectly challenging for the student's current ability level. It actually gets rewarded when the student fails.
So it's not just finding random hard stuff, it's finding the informative gaps. The things that challenge the predictor but aren't just impossible noise.
That's the magic of the min-max objective. If it picks something that's just pure noise, the predictor fails, but nothing is learned. It has to be a verifiable failure on a learnable concept.
And how do they optimize this?
They use something called generalized policy optimization, or GRPO. The technical detail that makes it all click is that the generator's advantage update, so the measure of how well it did, is just the negative of the predictor's advantage.
So if the predictor does badly, the generator did well. And if the predictor aces the test, the generator did poorly.
It's a perfect zero-sum game. It creates this seamless training loop where the student is constantly being pushed right at its weakest points, which drives this incredible generalized improvement without any external feedback. The curriculum writes itself.
Okay, if the model is constantly training on its own weak spots, the results should be pretty impressive. So let's get into the quantitative results.
The first thing you notice is the consistency. Across all their experiments, PretrainZero shows this stable, steady improvement over 2,000 steps.
Which is a huge contrast to the random RLPT baseline, right? I saw those graphs. The performance is all over the place. It spikes and then crashes.
Yeah, because it's not getting a consistently useful training signal. But the really crucial comparison is when you put PretrainZero up against traditional methods using that same low-quality Wikipedia data.
Right, like standard supervised fine-tuning, SFT, or just continuous pre-training.
And what happens is those methods often make the model worse. The Quen 3.4b model's performance actually dropped.
And not by a little. SFT caused a drop of, what, over 16 points? And continuous pre-training dropped by 8.
It just confirms something we've kind of known for a while. If you take a highly optimized model and then just dump low-quality supervised data on it, you can disrupt its internal distribution. You can make it unlearn good behaviors.
Which is what makes PretrainZero so remarkable. It uses that exact same low-quality data, but because of the active RL structure.
It successfully extracts high-quality supervision from it. It finds the needles in the haystack without disrupting the rest of the model.
And the numbers back that up. It improved the Quen model's overall average by more than 4 points compared to even the best passive RLPT baseline.
And on the really hard reasoning benchmarks, the gains are just massive. An 8.4-point jump on MMLU-Pro, almost 6 points on Super GPQA, and that incredible 10.6-point gain on the math average.
A 10-point jump in math ability from pre-training on Wikipedia. That's exactly the kind of generalized reasoning we want to unlock.
And here's the kicker, from a cost perspective. They did an ablation study, and they found that using the general, cheap Wikipedia corpus gave them better results for RLPT than using the specialized and presumably more expensive MathPile dataset.
Wait, really? The general data was better than the domain-specific math data?
Yes. It suggests the active method is so good at finding the informative gaps that you don't even need costly pre-curated data to build that foundational reasoning skill.
That's huge. So it's more effective and more cost efficient. But what about, qualitatively? Beyond the numbers, how does it change how the model actually thinks?
Well, this is where you see the emergence of genuine chain of thought. If you give a complex task to the model trained with random RLPT, it usually just gives you a direct answer. It's using pattern matching.
But the PretrainZero model,
It's a completely different process. You can see it explore multiple possibilities and analyzes them step by step. It uses the context to verify its steps, and then it summarizes its conclusion. It's not just predicting anymore, it's reasoning.
that's proof that the active masking objective is training a general reasoning loop.
For sure. But, the common critique with Emergent CoT is always efficiency. If the model learns to write these long, step-by-step answers, does that mean it's going to be slower at inference time?
A very fair question, and they actually looked at that.
They did. And for the same evaluation questions on MMLU-Pro, the final reasoning length was stable. In some cases, it was even more efficient than the base model's default CoT generation.
So the performance gains aren't just coming from being more verbose.
No, not at all. The improvement comes from a fundamentally better ability to predict and verify information. They improved the reasoning structure itself, not just the output length.
Okay, so you have this much stronger foundation. The final piece of the puzzle is to see how it holds up downstream.
The ultimate test, right? Do these gains actually stick around when you move on to specialized, domain-specific post-training?
So they took these PretrainZero trained models and put them through a standard RLVR process using a general reasoner recipe.
And the answer was a resounding yes. The gains persist. The PretrainZero models are just flat-out superior foundation models for any subsequent alignment or fine-tuning.
Let's look at the numbers for the Quin34B model end-to-end.
Right, so you take the base model and you give it 400 steps of RLVR. Then you take the PretrainZero model, which already had its 2,000 steps of RLPT, and give it the same 400 steps of RLVR.
And the PretrainZero version still comes out on top by 2.56 points on the overall average and 2.81 points on the math average.
Those are not small numbers after post-training. It means the active pre-training didn't just give it a temporary boost, it fundamentally improved the model's capacity to learn from downstream rewards. It makes all future training more effective.
So to synthesize all of this, PretrainZero really feels like a new blueprint. It breaks that data wall by pulling an active RL approach way, way earlier into the pre-training stage.
It's a fundamental proof that you can use RL to pull high-quality signal that leads to complex behaviors like chain of thought out of cheap, noisy commodity data. You don't necessarily need the expensive curated stuff to build a strong reasoning foundation.
And that kind of shifts the entire paradigm. It suggests we might not need ever larger, ever cleaner data sets. What we might need are just smarter, more adaptive learning algorithms.
The potential is already there. It's latent in the data we already have. We just needed a way to curate that curriculum on the fly to unlock it.
Which brings us to the final thought, the big question this paper leaves us with.
Absolutely. If you can get this kind of massive return on investment just by reframing standard masked language modeling as an adversarial RL problem, what else can you apply this to?
What other foundational self-supervised tasks could be framed this way?
Exactly. Could you do this with contrastive learning or denoising autoencoders or any of the other core pillars of self-supervised learning? It feels like the next wave of efficiency breakthroughs in AI might come from answering that exact question.